This film describes the mechanized production of proximity fuse amplifiers. The equipment is the outcome of a design study and investigation by ARDE into the logistics of such production. The work and manufacture was contracted out to Messrs. Plessey Company Limited, England. The electronic proximity fuse occupies the nose section of an artillery or anti-aircraft shell, and its function is to explode the shell when it approaches sufficiently close to the target. In this tiny space has to be packed all the components required for a miniature radio transmitter and receiver. These amplifiers have in the past been assembled and wired by lines of operators. The operations are time-consuming and wiring errors can easily occur. During the last war, thousands of these fuses were consumed each day, and in any future conflict, sufficient operators could not be found and trained to produce this and all other electronic equipment required. It was therefore decided that the production line must be mechanized. The first step was to redesign the amplifier and make use of a special form of printed wiring. An exploded view of the assembly shows the large number of components that have to be fitted into the small space available. Equipment was then manufactured to produce one amplifier every 12 seconds. 18 individually powered machines were grouped together to give a continuous product flow. The first row of machines print the circuit. The second pierce the circuit, produce end plates and complete the sub-assemblies. Components and valves are assembled, and the 4 final machines solder the amplifier, complete the assembly into the housing and perform electrical tests. The strip joining machine is the first machine of the circuit printing group. The base material on which the circuit is printed is a 10 thou thick Bakelite strip. This material is only available in lengths of 4 feet, and to facilitate handling through the subsequent processes, the strips are joined on this machine into continuous 500 feet lengths. The sections are removed from the magazine one at a time by a vacuum pickup arm and transferred to the work table. Here the control is taken over by vacuum pads on the table, and the strip fed lengthwise beneath a press which tacks a narrow band of resin glue film on the right-hand end. This end of the strip is stopped beneath the joining press, and a half-inch lap joint is. The two are joined together by pressure between the heated platens, the temperature of 150 degrees centigrade applied for approximately 12 seconds being sufficient to cure the resin adhesive and make a permanent joint. The glue film can be seen as the strip crosses the table to a reading device, where it's rolled onto a spool for transfer to the strip abrading machine. To provide a key for the later adhesive coating, the upper surface is abraded by carborundum shot blast, the effect of which can be seen on the top sample. The strip then passes through a chamber where the coarse particles remaining are brushed aside and collected for reuse. Before passing on to be re-reeled, a simple wire cage device operated by a loop in the strip is used to switch the reading motor on and off. This effectively adjusts the reading rate as the spool diameter builds up, and similar devices are employed on other machines in the line. The abraded strip is now passed to the adhesive coating and pre-cure machine, where 2 bands of Bakelite adhesive are applied. The adhesive is mixed in batches to a closely controlled specific gravity using MEK as a solvent. The adhesive level in the hopper is self-controlled, and the coating thickness is determined by the gate incorporated in the base of the hopper. In the first section of the oven, the strip is preheated by infrared lamps from below. This is done to avoid blistering the coating when the adhesive is partly cured in the second section of the oven, where the infrared lamps are placed above the coated material. The strip takes approximately 4 minutes to pass completely through the oven, and when it emerges, it's cured sufficiently to be non-tacky and can be safely re-reeled. It is then fed to the location hole piercing machine, whose function is to pierce a series of master holes which are used in subsequent machines for indexing and registration. At this point, a punch pierces the central indexing hole. Then a second punch pierces a series of 6 registration holes, the distance between the 2 punches corresponding exactly with that on subsequent machines. The strip is indexed by means of fingers which grip on the uncoated portion and feed it forward a fixed distance. A new datum is taken at each join by allowing the feed fingers to slip slightly. On subsequent machines, there is sufficient over-travel to accommodate the slight correction made at this point. The strip is now ready for circuit printing by a process utilizing silver powder, which is ideally suitable. Fine 300 mesh precipitated silver powder is loaded in the hopper. This is spread uniformly across the strip by a vibrating tray. A mask is used to keep the area of the location holes free of silver powder. Circuit is not printed on the area containing a strip join, and a cutout ensures that this section of strip is bypassed. The circuit pattern to be printed is engraved on a die attached to the hydraulic printing press. The die is heated to 160 degrees centigrade, and under a pressure of 7 tons per square inch, held for 5 seconds, the silver powder is compacted into the partially cured adhesive. The temperature, pressure, and printing time are all carefully controlled and related to the pre-cure of the strip adhesive. The surplus silver powder is removed by brushing. This is recovered for return to the hopper with a fixed proportion of new silver powder. The printed strip then passes slowly through a second infrared oven where the adhesive is completely cured, and when it emerges, the printed circuit is firmly secured to the base and is capable of withstanding considerable mechanical shocks. This completes the first line of machines in the circuit printing group. Meanwhile, the endplate molding machine is producing the polystyrene endplates to which the printed circuit wafers are attached. 3 top and 3 bottom endplates are molded at one shot and are held together by radial stalks or sprue, which facilitate mechanical handling. The endplates are transferred to a conveyor where they are taken to the magazine loading and despruing machine. They are fed in under the magazines, and as they are pushed upwards, the sprue is cut off. The fill magazines are transferred to the wafering machine. Meanwhile, the printed circuit passes into the component hole piercing machine, where a 25-ton press pierces at one blow the 300 holes required in a complete set of wafers for one amplifier. The strip is looped to the wafering machine to compensate for the intermittent action of one machine and the continuous action of the other. In this machine, the circuit wafers are blanked from the strip and assembled to the end plates previously molded. 2 end plates, one top and one bottom, are withdrawn from the magazines. Micro switches check the presence of the end plates, and in the event of failure, the machine automatically stops. At the blanking press, a complete set of wafers is blanked from the printed strip and pressed onto the pegs molded on the end plates. The 2 end plates now move under the riveting head, where the wafers are secured to the end plates. They then pass under the electrical test head, where a complete check is made for circuit continuity and possible shorts between adjacent conductors by a uniselector at the rate of 60 tests per second. If a fault is found, the end plates are ejected at the next station. Otherwise, they are collected in a magazine which, when full, is removed and placed on the component loading machine. This completes the first stage of the amplifier manufacture, the printing of the circuit connections, and the assembly of the end plates. Meanwhile, the component preparation machines are handling the components prior to assembly to the amplifier. For easier handling, the components are mounted on tapes. They are individually hand-fed to the machine conveyor. Now, as it's necessary to have the leads reasonably straight and readily solderable, this operation is carried out at the first station by a patented method. The capacitor leads are of phosphor bronze and are particularly difficult to straighten. The jaws close by centrifugal force and apply a known pressure to the leads as they recede. By suitable design of the jaws, this same motion can be used to give a simultaneous cleaning action. The component is then picked up by suction and dipped first into a flux bath, and then, after indexing, into a solder bath. The same action then takes place on the other side of the conveyor to flux and solder the other lead. During each cycle, the surface of the solder bath is wiped to keep it clean and free from dross. The components are then carried to a cropping station, where the leads are trimmed to length. At the next station, the component is electrically tested. If accepted, it then passes to the taping wheel, where it's fixed between linen tapes. If a component is faulty, it's ejected, and the tape wheel halts for one cycle to avoid a gap in the taping. Components supplied ready taped by manufacturers are run through a testing machine which automatically checks electrical tolerances using a comparison bridge and a known standard. Rectifiers are also checked for correct polarity. If any component lies outside tolerance, it is indicated by means of a staple placed in one tape. This staple is later detected in the component loading machine, causing the faulty part to be rejected. Miniature valves are received from the manufacturers in this state, and it's necessary to add a plastic button to the base, crop and bend the wires, and then insert the valve into a plastic sock for easy mechanical loading into the amplifiers. These operations are carried out automatically in the valve preparation machine. Valves are loaded one at a time by hand into the straightening combs. A plastic sock is loaded into the top table. The machine is started, and the combs come together and straighten the wire leads, cropping them to length. A polythene button is fed up the wires to the base of the valve. The machine then indexes to the second station, where the wires are splayed out and then formed at right angles. A heated tool seals the part where the wire leads traverse the face of the polythene button. The machine indexes to position 3, where the next head lifts, and crops all the wires to the same predetermined length. The valve moves to the 4th station, while the sock is indexed to the same station above it. A ram then pushes the valve into the sock. The assembly now moves to the test station, where the valve is checked. If satisfactory, it is then delivered to a collecting box. This completes the component preparation group of machines, which feed sequentially into the red block on the diagram, representing the component loading machine, which has provision for loading up to 48 components comprising resistors, capacitors or rectifiers, 4 valves, and up to 8 wires for connections between the base plate, amplifier, and transmitter. The holder and bottom circuit end plate are first placed by hand on the conveyor, which then indexes and, when it stops, lifts the holders into position. These loading heads are air-operated, and on the downward stroke, a component is cropped from the tape. On the return stroke, the tape is indexed forward 1 pitch, and the component raised by electrical solenoid into a loading breech. From here, it's delivered by air pressure down a flexible tube, which terminates in the correct position at the loading station. This sequence of operations occurs simultaneously at each of the 48 heads, and 4 components are loaded into the holder at each loading station. If any head encounters a reject component, the staple in the tape causes a uniselector to detect that particular head, which then indexes until a good component is available. After loading with a full number of resistors, capacitors and rectifiers, the conveyor then indexes the component holders to the valve loading stations. The first operation is to load a valve sock from the Syntron-fed magazine into the indexing table. The valve is then electrically tested, contact to the prepared leads being made through the castellations in the sock. The tested valve is then indexed to the loading position where, provided it's a good one, it's pushed out of the sock and into the component holder beneath. Faulty valves are automatically rejected. The component holder next moves to the wire feed heads where solder-coated copper wire for the interconnections is fed from reels. The heads are air-controlled and feed the correct length of wire into the component holder, where it's retained by a slight restriction in the polythene. The holder then feeds under a loading head, where a top end plate is withdrawn from the magazine having been previously transferred from the wafering machine. The completely assembled amplifier then travels to the end of the conveyor, where it's unloaded by hand for transfer to the amplifier soldering machine. Here, the component wires are soldered to their respective end plates by a plunger method. The operator feeds an unsoldered amplifier into the left-hand holder. A half-soldered amplifier would be turned over and a completely soldered unit removed from the machine. At the first station, the connecting wires are correctly positioned in the amplifier. At the second station, the 3 valve socks are given a coating of very thick flux to prevent distortion when they are immersed in the solder pot. At the third station, the surface of the amplifiers to be soldered is sprayed with pure rosin flux. Surplus flux in the spray chamber is drained back into a recovery bottle. The amplifiers are now ready to be soldered by a patented plunger method, the principle of which can be seen in a diagram. Movement of the piston downwards in the left-hand chamber causes the solder to travel along the lower passage and overflow in the right-hand chamber, bringing the solder into contact with the wires and circuit to be treated. By this method, clean solder is always brought into contact with the circuit. The amplifiers are lowered, and solder at 255 degrees centigrade is then pumped up to the circuit. A 3-second immersion time is given, then the solder is slowly withdrawn. This is to avoid short circuits and solder tears. During the index, the solder is pushed up to its top limit and automatically wiped clean. The amplifier is transferred by hand to the base plate assembly machine, which is the first of the green-colored section in the last group of machines. The operator places a base plate onto a loading ram. The base plate is then fed into the main turret and locked in position. The turret and the loading head both index, and the amplifier is fed into the base plate, the connecting wires entering into the hollow pins. The turret indexes twice before reaching the solder pot. Solder at 265 degrees centigrade is then pumped up by a system similar to that used on the previous machine. The turret indexes and the connecting wires are positioned correctly for the following stages. An insulated disc is picked up by a suction pad and lowered onto the amplifier. The turret moves to the wire-forming head, which is lowered onto the amplifier. A double wire-forming action then takes place at a pressure of 50 pounds per square inch. Finally, the amplifier is unloaded, a ram fitted with a suction pad is brought up under the base plate, and the unit lowered onto the transfer mechanism to the polythene potting machine. Amplifiers are fed at the rate of 1 every 12 seconds from the base plate machine to the transfer mechanism and delivered in pairs to the potting machine at the rate of 2 every 24 seconds. This is necessary to achieve adequate molding time. This machine encapsulates the now assembled amplifier in polythene, which serves both as a seal and as a means of supporting the printed circuits against movement and stresses set up by acceleration. Amplifiers are ejected from the tool in pairs, received by a transfer mechanism which transports and plugs them into sockets on the conveyor of the amplifier test machine. This machine carries out a complete electrical test on the amplifier and assembles it to a metal housing. The presence and position of the 5 through wires are checked at this station. If the amplifier is found to be faulty, the machine will reject it. A complete test is then made of all amplifier parameters by probes connected to a test set alongside the machine, and should a fault be found, the machine, obeying a preset signal, will reject the unit at the next station. Finally, the amplifier is loaded into its metal housing by a ram, and finished units are unloaded by hand and stacked for packing. The amplifiers are now ready for the addition of the oscillator assembly to complete the VT fuse monitor.